All right, guys, this video here is going to go over an application of the transformation data that you looked about in the last video, transforming data in the last video. So we're going to talk about that. And then we're going to talk about some distributions. So those are kind of the big chunk of 2.2 is going to be covered in this video here. So take a look at this first problem here. So it says in 2010, taxi cabs in New York City charge an initial fee of $250. Zoom in on these notes a little bit too. Okay, charge an initial fee of $250 plus $2 per mile. The distribution is skewed right with a mean of 4.8, or the distribution of distance for one businessman was skewed right with a mean of 4.8, the standard deviation of 2.3. Okay, so the question is what are the mean and standard deviation of costs of cab rides in dollars? Okay, so we're looking at this one businessman and we're trying to figure out the distribution. What is the mean and standard deviation of this guy's cab fare? All right. So right off the bat, I can write a little equation for calculating the fares. Right. So we have y equals 250. Right. That's the initial fee. Plus 2 times x or miles, whatever you want to call them, I'll put miles, right? And I just got this equation from just reading the problem, right? So you start with an initial fee of $250, so that's where the plus 250 comes from, and then we charge $2 a mile. That's where the 2x or 2m comes, or 2 miles comes from. Okay. So now, the next piece of important information when I look at this, right, is this businessman has a mean of 4.8 and a standard deviation of 2.3. Okay. And so we're trying to figure out what this guy's distribution of cost is going to be for the cab, right? So we're going to take this information and we're going to plug it into this equation right here. Okay. So now the question is, right? By looking at the or thinking about the notes from before, right? When I plug in this 4.8 for miles, right? That's a measure of mean. Am I going to add the 250 at the end, or am I not going to add the 250, right? So basically another way of putting that is when I do this transformation, does addition impact mean? Okay, and if you think back to the video last time, it's going to impact the mean, right? So I get to add this 250 on in additional to 2 times it. And then with the standard deviation, right, if you think back into the video, standard deviation, addition doesn't impact standard deviation, right? So you're going to be able to multiply by 2, but you're not going to be able to add 250. All right, so to calculate the mean, cost of the cab ride, so mean cost of cab, we can just go 2.50 plus 2 times the number of miles he does on average, which is 4.8. All right, once you simplify this down, you get to a value of $12.10. And again, in this class, right, everything's in terms of context, right? So that's why I wrote this as mean cost of cab is equal to $12.10. I just didn't give a number, put some context, right? So everything's going to be in terms of what we're looking at in this problem. Now the next one, what's a standard deviation? Okay, and with standard deviation, we just said you don't do the addition part. So to calculate the standard deviation, of the cost of the cab, standard deviation of right, you just do your 2 times, now we're looking at standard deviation, so 2.3. But again, addition doesn't change the shape of a distribution, right? Only multiplication does. So I'm not going to add on the additional 250. And this gives you a standard deviation of 4.6. So $4.60. Okay, so this is just kind of like a recap of what we did last time. We looked at in the last video. Again, multiplication and addition both impact measures of center. So those are your mean and your median. For measures of spread, which is your standard deviation IQR, it's only the multiplication, not the addition. Okay, that's the big thing to take away from this. Okay, now if we standardize each distance, what would be the shape, mean, and standard deviation of the distribution? All right, so when we talk about standardization, I've talked about it before. It's the idea of putting everything under the bell curve. And so what you do when you standardize is you subtract. So when you standardize, you subtract the mean from each value and divide by the standard deviation. Okay. Now, if you think about it just a little bit, when you subtract the mean from every single value and you were to add all those up, okay, what ends up with the mean is like your middle value, is your balance point. So if you add all that up, you end up getting 0 if you add up all those values. So when you standardize, you are shifting all the values onto the standard normal curve or distribution, which is another way of saying bell curve, which I think all of you at this point know what a bell curve is, or at least seen a bell curve, with a mean of 0 and a standard deviation of 1. Okay? So when we compute z-scores, you're doing a standardization process, where you're subtracting the mean, dividing by the standard deviation, you're putting it onto the standard normal curve, and as we're going to see in the next couple of problems, that leads to you being able to find probabilities, and probabilities are obviously kind of the point of this whole course. So that's kind of the reason behind all this. That's why we do this. So moving on to the next page. Okay, so this is a good question to think about. I'm not really going to go through this one. We can look at this in class if we have to, but just think about this one. So next thing, what is a density curve? So a density curve describes the overall pattern of a distribution. The area under the curve represents the proportion of all observations that fall within the interval. Okay. Think about those of you that have taken calculus before or know some calculus is like taking an integral. Just some basic information for you there. The sum, or let me put it this way, the total area underneath the curve, hopefully you can kind of figure that one out, is equal to 1, right? All probability distributions have to sum up to 1. It's just like a basic fundamental theory of probability. So the area underneath is equal to 1. And in terms of like, if you're going to graph a distribution, it is always located on or above the x-axis. So just don't draw below the x-axis. I don't know why you would, but yeah. So how do you identify the mean and median of a density curve? So visually, you can think about it this way. The median is the equal areas part. So if you were to divide the distribution in 2, you have the same area on both sides. versus the mean, which is the balance point of the distribution. Okay. So most famous distribution out there is going to be the bell curve. All right. So you have a distribution that looks something like this. That's a little skewed. I'm going to do that again. That's a little better. Okay. Now, when you have a symmetrical distribution, right, assuming this is like perfectly symmetrical, what you notice is that your mean and median are both the same value going right through the center. So you have the mu or x bar is equal to the median. And then your distance away from the mean, these are going to be your standard deviations. Okay. So what is a normal density curve? A normal density curve, I kind of talked about it on the last page. Okay, we'll give a proper formal definition. So a normal density curve describes the normal distribution, which is the bell curve. The mean is at the center, which is also called the peak sometimes. You can hear it both ways. The standard deviation is the distance from the mean to the inflection point. And what do I mean by inflection point? That's the part of the curve where it starts to turn. So I'll just draw it again. So here's your distribution. Okay, so this spot right here where it starts to turn from right here, so these inflection points on both sides, and then your mean is in the middle. So then this distance from here to here is your standard deviation. Okay, so it's a measure of distance. All right, so now it says here, according to the CDC, the heights of 12-year-old males is approximately normally distributed with the mean of 149 and a standard deviation of 9. Sketch the distribution, labeling the mean. Mean and the points 1, 2, and 3 standard deviations from the mean. So I'm going to draw a little, here's my x-axis. Okay, that runs on forever and ever and ever. I'm going to put my distribution on the x-axis, just above the x-axis. Drawing bell curves is really hard. Try your best. Okay, these things go on forever and ever and ever. Okay. And so the mean goes in the middle. So the mean was 149. Okay. And now our first inflection point, this is going to be where the next standard deviation goes. So we're going to go from here over this way. We're going over 9 centimeters. Okay, so that puts this value at 158. Then I go the opposite direction, go 9, again into the inflection point. Hopefully it's about even. So another 9, so now this point right here on the graph, this is 140. Now keep expanding that out. So the next one is going to be 2 standard deviations. Again, make it roughly the same width. So this is now 167. And then one more. 176. right? Again, I'm just going to keep adding 9. Add 9. Add 9. Same thing on the other side. Keep subtracting 9, so minus 9 here. And you get 131. And then one more. And you get to 122. Again, subtract 9 each time. And now we can label this a little bit more. We can go in here and use a different color. So this is minus 1 standard deviation. On this side, this is plus 1 standard deviation. So I can label all these sections and then do a different color. This is plus 2 standard deviations. This side is minus 2 standard deviations. Then one more. Plus 3 standard deviations. And minus 3 standard deviations. Okay. And we're going to talk about the empirical rule in a little bit. Okay. And that's going to be pretty important. But what you're going to find, as you guys may have seen this before in some of your other classes, but what you end up finding is that the distance from your that's 1 standard deviation away. So from -1 to +1 standard deviation, this takes up 68% of your data. Okay. And then if you keep going out, the next one, 2 standard deviations minus 2 standard deviations to plus 2 standard deviations. This is 95% of your data. Okay, and then we can do one more. I'll do it at the bottom just because of room. From -3 to +3, this is 99.7% of your data. Okay, so this is why when we talk about stuff like IQ and stuff like that, we don't really, the reason why we stop at 3 standard deviations is normally we don't really care about the last 0.3% or 0.15% on each side, right? So that's why we kind of stop at three standard deviations. Because once you get into those extremes, you get into outliers. All right, so let's keep looking at the stuff here. So here's a dot plot of 50 students with the distribution with a mean of 76.4 and standard deviation of 79. What percent of values are within 1, 2, and 3 standard deviations? I'm just going to write this out. We just kind of looked at it on the graph. So you have plus or minus 1 standard deviation equals 68% of data. And you plus or minus 2 standard deviations. That's equal to 95% of data. And then you have plus or minus 3 standard deviations is equal to 99.7% of data. Now, the nice thing about this is that these distributions are normal, or are symmetrical, sorry. So you can divide each one of these into like different pieces. So just do a quick example. If I looked at the bell curve, normal distribution, okay, so here's my mean, right? And I said between -1 and +1 standard deviation is 68% of data. So this whole thing is 68%. Well, this thing is symmetrical. So if I just looked at half of it, if I just looked at just this half, what's that going to be? That's just going to be 34%. Okay. So you can kind of divide each one of these pieces into little chunks. Okay. And then 34 on the other side as well. So then this side would also be 34%. Okay, so these are symmetrical distributions. So that means you can kind of divide everything up in half, and you can get all these little percentages. Now, I guess one other thing I can point out is, and you can kind of think about this too, and we'll talk about this in class. If I go from the very beginning to the middle, what percentage of data is that going to be? Okay, think about that. Right? If I go from the very beginning of the graph, right? These graphs technically go on forever and ever and ever. But if I go from the very beginning to the middle, what percentage of data is that going to be? And think about that. Okay, moving on to the next couple of things. What is the 68, 95, 99.7 rule? When does it apply? So in a normal distribution, kind of just restating what we've just been working on, with a mean of mu, that's the Greek symbol, and standard deviation. I can't do the symbols in here, so I'm just going to put sigma as I'm typing. That's a little circle with a line on top of it. Then what can we say? We can say a couple of things. 68% of data fall within one standard deviation of the mean. 95% of data fall within 2 standard deviation of the mean. 99.7% of all data fall within 3 standard deviations of the mean. Okay. And again, big point here, this is only for normal distributions, okay? As soon as we get to non-normal distributions, which is what the next point is going to talk about, Chebyshev's inequality, okay? Yeah, so we don't have a normal distribution, we can't use these rules. So this is only for normal distribution. So when we get to further on, we talk about sampling techniques, we really want to focus on, is this going to be a normal distribution or not? Is our sample going to be normal, okay? So Chebyshev's inequality, this is it's kind of an expansion of the normal of the 68, 95, 99.7 rule. This rule also, by the way, is called the empirical rule. Okay, it's another word for it. So the Chebyshev's inequality is an expansion of the empirical rule. And what this does is it can be applied to any distribution. Your distribution does not have to be normal. Right, so you can have skewed data, which is nice because you're lucky in life to get normal distributions. And then this shows this inequality will show the proportion of observations that fall within K deviations. Okay, and so that's the technical definition. What this means is the formula. You have 1 minus 1 over K squared. Where K is going to be the number of deviations you're looking at. Okay, so where K is the number of deviations you are concerned with. Okay, so for example, let's say you don't know the shape of your distribution, right? But you want to know what percentage of your data is going to fall within 2 standard deviations. Okay, so then I say K equals 2. So I don't know the shape, or don't know anything about it. I didn't decide to graph it. Or I did graph and I found out it's skewed. Okay, so what percentage of my data is going to fall within 2 standard deviations? So I can just plug this 2 in for k down here. So I get 1 minus 1 over 2 squared, which is 1 minus a quarter, which is equal to 3/4. And so the way you interpret this is that at least 75% of your data is going to be with at least 75% of your data is going to be within 2 standard deviations, no matter of the shape of your distribution. Okay. Any questions on that? Okay, so moving on to the next one. So using the earlier example, about what percentage of 12-year-old boys will be over 158 centimeters tall? Well, I'm going to do this 2 different ways. I'm going to do it with if it's normal and if it's not normal. So if it's normal, so if normal, okay, we have the mu is 149. Standard deviation, that's sigma, by the way, is 9. And if it's normal, we can use our normal equation, which is z equals x minus mu divided by standard deviation, which is in this case 158 minus 149 divided by 9, which equals 2. Okay. Now, if I'm looking at this on the distribution, okay, if I'm drawing a picture, all right, so here's 158 in the middle, or sorry, not 158, 149 in the middle. This is 1. Oops, that's supposed to be 1. Sorry. And then 158 is 1 standard deviation away, so 158 is right here. Okay, so this is 1 deviation. Okay, so now we can use our empirical rule. If it's normal, we can use our empirical rule. Okay, and well, what do we know? Well, we know that from the beginning to the end, this is 50% of data. Okay, so from the beginning of the graph to the middle is 50%. And we said we can divide up each one of these chunks into little halves. We know this is 34%, right? Because when we look at plus or minus 1 deviation, that's 68%. Go from here to here, this is 68, so half of it is 34. So if I'm looking at the beginning all the way to this spot right here at 158, that's going to be 50, this 50 right here, 50% right here, plus the other 34. Okay, and that makes 84%. But here we're looking at the probability that it's going to be over 158 centimeters tall. Okay, so 158, this is 84% is going to be from 158 and below, right? And what did we talk about earlier with the area under this curve is going to be, the whole thing's going to be 1. So all I have to do is go 1 minus 0.84, or 100 minus 84, and you get 16. So there's a 16% chance that a 12-year-old boy will be over 158 centimeters tall. Okay, moving on to the next one. About what percentage of boys are going to be between 131 and 140? Okay, so I'm going to draw a graph again. So we had 149 in the middle. Okay, we have 140 is one deviation below. And then we got one more deviation below that, it's 131. And so graphically, what we're trying to find is this little area right in here. Okay, we're gonna try to find this area right here. Okay, well, so how could we do this? Okay, so we can look at a couple things, right? The way I would do it is subtract, oops, I was supposed to do that. I would subtract some areas away from each other, right? So what I would do, we're trying to find this pink area in here. What I would do is I would take this whole green area, so from this middle all the way down to the end, okay, take that green area, okay, or sorry, yeah, you could do that, or you could do from 140 down to the end, right, so this orange area, and then subtract away, you're gonna have to subtract away this part here in the blue, this very end piece right here, okay. That's kind of what we're trying to do with this, all right, so we're looking at, let me clear these. So here's 149. So we said this right here was 34%. Okay. This is 140. Right, and then we had the next one, 131. And from here, two standard deviations, we said this was 95%. It's plus or minus 2. So how much is going to be in this little chunk right here? Well, there's 5% total on each tail, so this is going to be 2.5%. Okay. And so now we're looking at this area in between, right? So from the beginning to the middle, this is 50%. And then from the beginning to here, this is 50 minus 34. Right, because I got this for the 34 from the 140 to 149, which is 16%. Okay, and now I got this 60. I got this 16% minus this 2.5. So to get this area in the green, I have to do 16 minus 2.5. Right, so I'm just breaking everything down into different chunks. And so the probability that a 12-year-old boy will be between 131 and 140 centimeters tall is 13.5%. Okay. So I'm just taking this whole distribution, I'm using the empirical rule, just dividing it into different sections and then dividing things in half because everything's symmetrical. So if I know this whole first half, or if I don't know from plus or minus 1 standard deviation is 68%, I know that half is 34. Okay, I know the whole thing from the beginning to the middle is 50%. So 50 minus 34 is 16. That's how I get to 140. So I know this is 16%. It's that 16% is going to be below 140. I can do the same thing with 131. That's 2 standard deviations. So that's 95%. That means 5% on either end. Divide that in half. I get 2.5%. Subtract away to get the middle, and you get 13.5. So definitely take some time to draw those out. They're definitely confusing when you start looking at all those different chunks. Definitely take your time to do that. Okay, so now the next, last 2 questions here for this video. suppose that a distribution of test scores is approximately normal, and the middle 95% of scores are between 72 and 84. What's the mean and standard deviation of this distribution? Same thing, I'm going to draw a picture. Okay, so we know that your mean is here in the middle. We know that we have 1 standard deviation, 2 standard deviations is at 84, and same thing below, we have 72. So 1 and 2. Okay. So now the question is, what is going to be this middle? What's going to be the mean and standard deviation? So and we know that this distribution is normal, and we're going to say that it's because it says it's approximately normal. So we know that everything's going to be spread out equally. Okay, so how can we divide this into equal chunks, right? And what you find out is that those equal chunks are of size 3. Okay, so if I go here at 75, 78, 81, and then 84. Okay, so I just did this and just divided it into equal chunks, into equal parts. Okay. So we have 1, 2, 3, 4 chunks, and we have a distance of 12. So 12 divided by 4 is 3. That's all I did. Okay. And so now you've kind of figured out all these chunks. You can know that the mean is 78, and your standard deviation is 3. Okay. Now remember, we can only do this because this is a normal distribution, right? Because it's normal, we can say that these things are symmetrical. Because it's symmetrical, I can take a look at the values from 72 to 84. That's 12 points. Divide it into my equal chunks of 4, and I get a value of 3. Okay. And so now calculate can you calculate the percent of scores that are above 80? So 80 is right here. Okay, so here's 80 on the graph. So it's asking, can we figure out this percentage over here? Can we figure this out? Based on the information I've told you so far, not yet. Okay, so right now, so as of right now, we cannot calculate this. Since we only know the empirical rule, and 80 does not fall on a whole deviation, we could not determine the probability. This is where table A or a calculator will help. Okay, so this is coming. This is what's going to happen in the next couple of lessons. Okay, so that's the end of this video. Kind of a longer one, looking at distributions. As always, if you have questions, please let me know. And yeah, I'll see you guys in the next video.